Okay, this is our flipped classroom for section 6.3 on integration by parts. And the resources you're going to need for this are the PDF, which is on the web page, the Greg Kelly PowerPoint, and that link's there, and also the Khan Academy link, where Sal Khan goes through the derivation of the integration by parts algorithm. You actually would like to, you may want to pause the video now and watch the Sal Khan video, and then come back where we're going to pick up. We're going to, just briefly go over what he got, and probably more helpful for you to watch his video, which is only 10 or 12 minutes. In the video, he's using f of x and g of x, and we're using mu and v. So they're interchangeable, just so you understand that. And we're going to go through, well, this video we're going to go through 3 textbook examples, 2, 5, and 4. I'm going to ask you to do 2 problems in the exercises. After you do example 2, you're going to do exercise 5. And then we're actually going to do that problem by a different method. And then after you do example 4, we're going to ask you to do problem 17. So here is the algorithm for integration by parts using mu and dv. So this is the end game. This is the algorithm you're going to apply, which is the integral of mu dv equals mu times v subtract the integral of v d mu. And where's it coming from? Briefly, from chapter 3, it's coming from the product rule. So if you have mu v, the product of mu v, and you're differentiating that, you're getting mu dv plus v d mu. Then you turn around and integrate that line. On the left side, that would just take you to mu v. And on the right side, you would integrate this sum, and you would get the sum of these 2 integrals. And then we're adding the opposite of this to both sides, which is going to leave us with just this, which is the integral of mu dv is equal to the product of mu times v subtract the integral of v d mu. This is that. Now, integration by parts is a topic that's specific to BC. It isn't on the AB test. And the tabular integration, which we're going to do with, we're going to apply to example, which is example 5 in your textbook, is a shortcut that works if one of the factors differentiates to 0. So, here's the topic that you're accountable for in the test. In the textbook, they give you this mnemonic when you're trying to decide which of the factors you're going to assign to mu and which one you're going to assign to dv. So they're telling you in this order. So in example 2, we're trying to integrate the product of x squared e to the x dx. And we end up with, okay, in my order of choice, here's polynomial. So we're going to call mu x squared. And across this line, we're going to differentiate. So we end up with d mu equals 2x dx. The other factor, e to the x dx, is our dv. And as we go across, we're going to integrate that, and we end up with v equals e to the x. So here's our question. Our question is going to be equal to mu times v. X squared e to the x. Subtract the integral of e to the x times 2x dx. Take the 2 out in front of the integral, and now we have to reapply the technique to what we have left. And for what we have left, we're going to assign mu equals x. We differentiate across. dv is e to the x dx. We integrate, we get e to the x. So then we pick up from where we were. So we're going to take this branch right here and just reapply. So we're here, and we're going to say, okay, this thing is going to be equal to, the integral of x e to the x dx is going to be equal to mu times v, which is x times e to the x. Subtract the integral of e to the x dx, which is just e to the x, plus our constant of integration. So the answer is going to be equal to, here's the original question, x squared e to the x, and you're taking a negative 2 and distributing over what we got here, which is going to be negative 2 times x, negative 2x times e to the x, and this negative times a negative would give you plus 2 e to the x plus your constant of integration. So that's your model. You can back up the video and watch this again if you wish. But you're going to try and take this and apply this and do exercise number 5. You're going to pause the video, do problem 5. We're going to pick up from there. Okay, for problem 5, we're trying to integrate x squared cosine x dx. So we're going to assign x squared to mu, and then as we go across this line, we're differentiating. That means what we have left, the other factor, cosine x dx, is our dv. And we're going to integrate that and end up with sine x. So here's the question, and what do we expand that? We're getting mu v, which is x squared sine x, subtract the integral of v d mu, which is 2x sine x dx. We just put the 2 outside up front of the integral. But then for this branch of our answer, we're going to have to reapply. So u is x, sine x dx is our dv. This line across, we're integrating. We're going to end up with d mu equals dx. This line, as we go to the right, we're going to have to integrate. We end up with negative cosine x. So this branch alone of the problem this branch is going to give us mu v, which is negative x cosine x, subtract the integral of v d mu, we're here. You have subtracted negative there, which is, we change this sign. Now we're saying what? Here's the original question. The original question is equal to this, x squared sine x, subtract this line. So I'm subtracting a negative. So I rewrote that as plus 2 times this, and then distributed the negative in front of that. Because when we integrate the cosine x, we're sine x. Plus the constant of integration. We just distribute the 2 over everything, and this is what we end up with. And you have to be sure to include the constant because we did an indefinite integral. Now, your textbook, if we go back to example 2, the textbook takes the same problem from example 2 and solves it by tabular integration. So here was the question. Example 5 and example 2 are the same thing. This technique will work if and only if one of the factors differentiates to 0. So we pick that factor, which we can tell that x squared is going to, as we differentiate this, it's going to go to 0. And we take the other factor and we integrate it. So x squared, differentiating it, 2x to 0. E to the x dx, we integrate it. We're just going to have e to the x's. The book does it with diagonals, but what we're saying here is we start one line later, if you want to look at it that way. And then these signs alternate. We're multiplying across. This times this, it's positive. This times a negative 1. this times a positive 1. They're your terms. So I would have x squared times e to the x plus a negative 2x e to the x plus a positive 2e to the x plus the constant of integration, which you know this is a much more efficient way of doing the problem in example 2. Now, we're going to move on to example 4, and then you're going to have one more problem to do. So in example 4, we've got the indefinite integral of e to the x cosine x dx, and you see that it's not a candidate for tabular integration. We're going to assign, going by the guidelines, e to the x, the exponential function, so we're assigning that to mu. We differentiate it across. Cosine x dx is our dx. So we're integrating that, and we're getting to sine x. So the original question is going to be equal to mu v, which is e to the x sine x, subtract the integral of v d mu, e to the x sine x dx. And it might not seem that we made progress, but same thing, just like sunscreen, we're going to reapply the algorithm, and we're going to say, okay, just this branch right here. Mu is e to the x, differentiate across. dv is sine x dx, we're going to integrate that and get negative cosine x. So now, this branch right here is equal to mu v, which is here, subtract, integrate v d mu, which is here. And if we go to the original problem, the original question is equal to, from the first branch, e to the x sine x plus e to the x cosine x, right here, we're subtracting the negative. This is subtracting the negative, then we're subtracting the whole thing, so that's subtracting this branch right here. Except if you notice, this is the left side, that's the question. So if we add this to both sides, we're now here. 2 times the question equals just the right. Divide both sides by 2. Now this is the constant of integration. So, c and c over 2 would be the same thing. Not the same value, but we're not putting a value in for this. And then if we factor out an e to the x over 2 times this plus your constant of integration. So this is the same technique you're going to use in problem number 17. So you're going to pause the video, go to 17, and then we're going to go back to that solution. Okay, so when you went to problem 17, you would notice that it's very similar to the example. The difference being you have sine x is one of the factors. So we're not going to go through the mechanics of the whole derivation. You can look at the PDF to see it. Here's our mu to start with. Sine x dx is our dv. Differentiate on that line, integrate on that line. Then we're going to rewrite that, and we're going to have to reapply the technique, just like you did in the textbook example. And reapplying the technique was going to get us to here. But it's the same thing as you did in the example, that after you apply this the second time, what is to be integrated ends up being the question. So if you add it to both sides, you're subtracting it here, so you add it to both sides. You have 2 times the question equals the right side. And then this was a negative sign, so we just reverse the order of these two. That's the commutative property of addition. Divided both sides by 2, you have your constant. And this answer is fine, or we can rewrite it like this. So when you get to class, if you need some of the problems in more detail, you're going to put them on the board and we'll go through this.